Hello, my name is Bo Brixon, and I am presenting the much anticipated coin toss project for CSC 110. And so I'll just get started. So, what this presentation will include: an overview of the process regarding the creation of my code, review of the code as well as an explanation of how it works, and the results the code produces. The process. I had been working on this code for a long time. Between reading the book, researching online, and getting some help from my friends, I was able to refine my code into something reasonable and usable. My original code was lengthy and inefficient, and I'll probably get into that later. Yeah, I just did a way longer code than I had to at first, and that's part of what going to the classroom was really helpful for. Is between friends and stuff, I was able to get it down to something usable, and realistic, really. So, A. Use the random module to simulate the experiment of tossing a fair coin n times for n equals 5, 10, 20, 50. So here's the code. Some of the basic things here, self-explanatory. I'm importing the random module. Call it flip, probability times, initialize an accumulator, essentially, head counter, tail counter, and then a for loop for I in range times, depending on how many times the user inputs into the parameter. And then one flip equals random, and if one flip is less than whatever probability that's given, which in this case is 0.5, then if it's less than, it goes to the head counter accumulator. If not, it goes to the tail counter accumulator. And then I just return both the head counter and the tail counter. Here are the results of that. As you can see, I put in 0.5 and then 5. Got 2, 3. In this case, I got 2, 8 out of the 10. And I got a perfect split on both 20 and 50. 10, 10, 25, 25. B. Simulate repeating the above experiment n times. For each value n above, use m equals 1000 n, 10,000 n, and 100,000 n. So here's the code I created, especially for this part of the project. Is kind of self-explanatory on how I did this here. I just made the loop go through both of these, and which includes the function from before. So A was a helper function to this one, obviously, and there it is. And here's the results, and as you can see, everything looks pretty realistic. It's a pretty even split. Everything is about where it should be for the amount of times that the coin was flipped. Out of this 500,000 times, look at that, almost 250,000. Out of 10,000 times, almost 5,000. So it's about perfect. C. For all 12 combinations of m and n, compute the probability that there are nh heads and n minus nh tails, for 0 is less than equal to nh, which is less than and equal to n. This will be the relative frequency of nh heads and n minus nh tails within an experiment. D. Repeat the above computations using an unfair coin with the probability of heads equaling 0.52, 0.55, and 0.60. For each of the 48 cases, write out a file with your results, neatly organized and labeled, and using a format identical to the file I created, probability outcomes predicted txt. Write out a second file computing the error, simulated probability minus predicted probability, and the relative error, divided by predicted probability times 100 for each case, and using the same formatting. Use coin toss prompt or probability outcomes predicted txt together with your simulated data. Here's some of those helper functions, some of which were included in the website along with the project, as you can see here. But yeah, all which I use and incorporate these in this, the bread and butter, the one code to rule them all. And here it is. So I call it coin toss. I make the out file, go to cointossproject.txt, and I have it append. Initiate an empty dictionary and prob sim and probability predicted. And then I just make some loops, for I in range, n, which is given here, to the dictionary, another for loop, including the helper function here, which I, associate to h, which I make the loop. And then, yeah, for the most part, a lot of this is the formatting, which I will show you shortly here. I made it look nice and clean, and I actually combined the two, so I just kind of made it easier for you. And in class, I don't know if you remember, but you mentioned that it would be a lot cleaner and better if it was just created in the way that you showed, which was in just one big bar. So I tried doing that same thing. So I just had it all laid out, which I'll show you soon here. And then here's another for loop. Determining the error. You see here you told us how to do this, which was error divided by predicted times 100 for the relative. You can see right there, and here's some more of the formatting that lines up with these columns, which I will show you soon. And then here is the really probably one of the most important parts here, which I really wish I would have figured out in the beginning. What I was mentioning in the beginning when I said that it was a tedious process and I had made a very inefficient code is I had actually written out something a lot like this. I had done like a loop, but then put a whole bunch. I don't know what I was thinking. I don't even know what. I must have been tired that day, but and I'll include that too when I send it to you, just so you can see what I went through. But anyway, this was obviously the way smarter way to do this. It's just a loop within a loop within a loop, and then I put this function right there, so it just runs through all these. And then I was saying that I would include the results into this, but it wouldn't fit in this presentation, so I guess I will I'll show it to you right now. I'd already ran it because it took a very long time. Well, I guess not very long. It took a good 5 minutes or so. And as you can see, this is pretty much the same that you showed me in class, like to have it laid out just like this. Here's fair coin, simulated probability, predicted probability, error, and predicted relative error. And you can see, everything about makes sense here. Yeah, okay. So then, and then here's a unfair coin going off of 5 tosses. And so, you get the idea. It's very long. You can see over here on the scroll bar how long this is, just so you get an idea. And then all the way down to when it starts flipping the coin 50 times. Right there. So, and I'll send that too, so you can look over that if you want. And then, G, discuss how you might use the above results to determine if a coin is fair. In order to determine whether or not a coin is fair, I would assess the correlation between the simulated results of tossing a coin and the predicted probability associated with the fair coin to see if the margin of error lands within the criteria for what is established as fair. If it is apparent that the results of the coin in question were within the predetermined margin of error, then it would be safe to assume that the coin is fair based off the given data. That is the pretty much, I guess, the more scientific or professional sounding way of answering that question, I guess. So, that's that. That is the presentation, and then I'll just go ahead and send you the code and send you the TXT file. Alright, thanks.